Okay, for another intermediate value theorem example, we're going to look at problem 2.8, number 13. So this one says, prove that 2 to the x plus 3 to the x equals 4 to the x using intermediate value theorem. So we're going to note that 2 to the x plus 3 to the x equals 4 to the x. That equation, we could say, we could move the 4 to the x across and say, let's look at 2 to the x plus 3 to the x minus 4 to the x equals 0. So if we can show a function f of x equals 2 to the x plus 3 to the x minus 4 to the x has a 0, or has, let's say it this way. We can show that the function f of x equals 2 to the x plus 3 to the x minus 4 to the x has a solution to that function equaling 0, then that will be equivalent to showing 2 to the x plus 3 to the x equals 4 to the x has a solution. So let's look at taking our function here, f of x equals 2 to the x plus 3 to the x minus 4 to the x. This is an elementary function. We know that 2 to the x is continuous, 3 to the x is continuous, 4 to the x is continuous. And adding continuous functions together is continuous. Subtracting a continuous function from continuous function is continuous. So we know f of x is continuous. And now we'll need to do a little bit of scratch work, because what we need is we're trying to show that f of x equals 0. If we can show f of x equals 0 has at least one solution, then we can show that 2 to the x plus 3 to the x plus 4 to the x equals 0 for some c value, and then that will prove that 2 to the x plus 3 to the x equals 4 to the x will be true for some c value. So basically, I need a value here where some x's are, so I need 2 to the x plus 3 to the x minus 4 to the x. I need this to be positive somewhere, and I need this to be negative somewhere else. So I'm just going to try, let's build a table of values and just start looking at some values. So let's go to, I'll do this in Desmos so y'all can kind of see it a little easier. Let's see here, Desmos, so we'll say 2 to the x plus 3 to the x. Oops, sorry, just kidding, I want to make a table. We're going to add in here, we'll add in a table, and we'll say, all right, I need 2 to the power of x1 plus 3 to the power of x1, and then I need minus 4 to the power of x1. Let me make sure I've got this entered correct for the equation. The equation was 2 to the x plus 3 to the x minus 4 to the x. That should be okay. So let's look at x1 being 1. We get 1. What about if we're 0? We get 1. Negative 1 gives us 0.5. Negative 2 gives us that. Let's see. Maybe we can get to some negatives. Nope. Okay, let's look at some bigger values. Let's say, what about 2 or 3? Okay, 2 gives us negative 3. That's what we want. So we're going to use like 1 and 2. So 1 is positive 1. That's a positive number. 2 is negative 3. That's a negative number. So we know between the positive number and the negative number, since this function's continuous, it'll have to pass 0 somewhere in between there. So we will say, let's note f of 1 equals 2 to the first plus 3 to the first minus 4 to the first, which is 2 plus 3, which is 5, minus 4 is 1. F of 2 equals 2 squared plus 3 squared minus 4 squared, which is 4 plus 9 minus 16. 4 plus 9 is, what is that? 13. 13 take away 16 is negative 3. Okay, so we were looking where is f of x equal to 0, and we now have a positive number, f of 1 is 1, and we have a negative number, f of 2 is negative 3. So let's say f of x, it's continuous everywhere, so f of x is continuous on the closed interval 1 up to 2. And furthermore, f of 1 equals 1, which is not equal to f of 2, which equals negative 3. So then, by the intermediate value theorem, there exists some c, an element of the open interval 1 up to 2, such that f of c equals 0. So f of c equals 0 means 2 to the c plus 3 to the c minus 4 to the c equals 0. So the intermediate value theorem guarantees us that there is some c such that 2 to the c plus 3 to the c plus 4 to the c equals 0. Well, we should say, I think I wrote there exists some c, and I really should say there exists at least one c. So instead of being kind of vague with some, the statement says at least one, so we should use at least one. So there exists at least one c in 1 to 2 such that f of c equals 0. Since f of c was 2 to the c plus 3 to the c minus 4 to the c, that equals 0. So we can rearrange this by pushing the 4 to the c across. So 2 to the c plus 3 to the c equals 4 to the c has at least one solution for c, an element of that open interval 1 up to 2. And that should do it. So we use the intermediate value theorem, and that proves that we got proved that it was continuous over the closed interval, proved the endpoints were different. So the intermediate value theorem guaranteed us there was at least one c such that what we wanted happened, and then we could rearrange what we got back from that. We could rearrange it to do the case that we wanted. So we'll stop that one there.